Here's a nice result I wanted to show you guys. So I have a question. How many multiplications would you need to calculate a sum of products? For instance, 35 times 46 plus 17 times 29. Now, we might think we need 8 multiplications, and let's see why. Well, we take 6 multiplied by 3, 6 multiplied by 5, 4 multiplied by 5, and 4 multiplied by 3. So here, we would need 4 different multiplications. And similarly, 9 times 7, 9 times 1, 2 times 7, and 2 times 1 requires 4 more. So in total, 8 multiplications. Now, let's try this. Let's calculate out this sum of multiplications. And, 6 times 5 is 30, 6 times 3 is 18, carry the 2, 21. So, this is a very standard calculation. And if you calculate this out, we get 2,103. And indeed, we needed 8 multiplications. Well, what if I told you we can actually do this in 7 multiplications? This video is about how to do this in 7 multiplications. It's a very, very simple problem, but in order to solve it in 7 multiplications, we'll need a little bit of algebra. So what we're going to do is we're going to recompute this sum of multiplications, but let's do it in a very weird way, a way that I've never seen anyone else calculate this. First, we will not do any carries when we add until the very end. So 6 times 5 is 30, 6 times 3 is 18, 4 times 5 is 20, 4 times 3 is 12, 9 times 7 is 63, 9 times 1 is 9, 2 times 7 is 14, and 2 times 1 is 2. So we're going to write that out, and we don't carry anything. Now, second, instead of adding down, we're going to add across first, and then we're going to add down. So we're going to take 30, and we're going to add it to 63. We're going to take 18, we're going to add it to 9, we're going to take 20, add it to 14, and 12, and add it to 2. So that gives us 27, 93, 14, and 34. Finally, we're going to add down the rows, the columns, and we're going to now apply our carries. So 3 comes down, and 9 gets carried over. 9 plus 7 plus 4 is 0. Carry is 20, so we carry the 2. 2 plus 2 plus 3 is 7, so we carry the 7. And 7 plus 14 is 21, and magically we recover our 2103 value. But we did it in a very strange way. Okay, so why did we do it in such a strange way? Well, let's look at the intermediate calculations more closely. Okay. So we're going to write this out again. 35 times 46 plus 17 times 29. Okay, but let's look at this array of numbers, 18, 30, 12, and 20. We can actually get this array of numbers by doing an outer product. And similarly, we can get the array of numbers that we get when we multiply term by term, 17 and 29. So we can get the array 9, 63, 2, and 14 with an outer product. And the outer product, to get the outer product, we just look at our 46, and we reverse its order. So writing 6 and 4, and we take 35, and we write it out. Now, let's double check. 3 times 6 is 18, 3 times 12 is 12, or 3 times 4 is 12, 5 times 6 is 30, and 5 times 4 is 20. That is exactly the array. Similarly, the outer product of the vector 9, 2 with 1, 7 is the array 9, 63, 2, 14. Adding these two arrays together recovers our array that we got before, 27, 93, 14, and 34. So, adding the arrays together is equivalent to adding across, as we did before. We take 30, we add 63. We take 18, we add 9. We take 12 and add 2. And we take 20 and add 14. Let's copy the array we had before and compare them to double check that they're the same. And voila, check this out. 27, 93, 14, 34. And then lastly, we pad the bottom row of our array with 0, and we add down the array, applying our carries. So we get 3, carry the 9. We get 0, carry the 7. And we get 21. So that gives us our 2103, just as we had before. So let's summarize. So what we've discovered is that we can do our sum of multiplications by doing the outer products, by calculating the outer product with 6, 4 and 3, 5 and 9, 2 and 1, 7. Now, the sum of two outer products is actually a matrix-matrix product. So we can actually compute all the required multiplications by multiplying the matrix 6, 9, 4, 2 with the matrix 3, 5, 1, 7. Both of these matrices we get directly from the integers that we multiply. Now, the reason why this is interesting is because it turns out we only need 7 multiplications to multiply 2 by 2 matrices. So we actually have just reduced our problem from requiring 8 multiplications to requiring a single 2 by 2 matrix multiplication, which only needs 7 multiplications. Now, if you want to know the result, it's actually Strassen's algorithm, so I've copied and pasted it here. You can just search Strassen's algorithm from Wikipedia. And I highlighted the sections here. So M1 through M7 are the multiplications that you'd require to multiply the 2 by 2 matrix. And C1, C12, C21, and C22 is the resulting matrix, which can be obtained by just adding up those M1 through M7 terms. Okay. Now, so we've reduced 2 by 2 matrix multiplication. We've reduced the problem of adding the sum of 2 multiplications from requiring 8 multiplications to requiring 7 multiplications. This doesn't seem like a lot. We just reduced a single multiplication. But it turns out when your dot products become very large, this actually becomes pretty useful. For example, let's say we don't want to add just 2 terms. Let's say we want to add 6 different terms. So 13 times 27 plus 56 times 38 plus 97 times 83 plus 72 times 64 plus 88 times 29 plus 93 times 44. So another way to write this is the vector-vector product 13 of the vector 13, 56, 97, 72, 88, and 93, which is a 6-dimensional vector, and the vector 27, 38, 83, 64, 29, and 44, also a 6-dimensional vector. So this is a vector-vector product, also known as a dot product. And this is a centerpiece of algorithms, machine learning algorithms, physics algorithms, simulations for PDEs and ODEs. Huge, very important calculation. And we have just discovered that we can do this dot product with a matrix-matrix multiplication. Here, since we have 6 terms that we're adding instead of just 2 terms, our matrix is going to be 2 by 6 dimensional. And we get it by taking the bottom numbers, 27, 38, and so on, and writing them in reverse order, so 72, 83, 38, 46, 92, 44, and then taking the top numbers and just writing them across, 1, 3, 5, 6, 9, 7, 7, 2, 8, 8, and 9, 3. So you can, so this is a 2 by 6 multiplication with a 6 by 2 matrix multiplication. and this can be computed with 3 2x2 matrix multiplications. This would require us 21 multiplications instead of the previous 24 multiplications, which would save us 10% on compute. This could be pretty important, especially for big calculations. One other thing I wanted to note is if your numbers that you're multiplying are larger, you can actually use larger matrices, which could also improve your matrix multiplication. For instance, let's say we want to multiply 345 by 517 plus 968 by 124 plus 778 by 554. This would give us a 3 by 3 matrix. This could be done with a 3 by 3 matrix multiplication. Okay, thank you for your time. Now, if you know of this result, please let me know in the comments, because I believe I may be the first one to know this, and so you are now the second.